Okay. The first question is super easy. Let's compute that limit. Limit when the x comma y approach to 6,3 of the function. Okay, the function is x times y cosine x minus 2y. This is my function. Okay, and you will need to compute this limit. I can see, for example, we have here a polynomial function, continuous. We have here trigonometric function, cosine, continuous. And the multiplication to continuous, continuous. Entonces, just plugging in. Si the answer is no undeterminate, que es a number, the answer is the number. End the story. Entonces, the answer is, use substitution, plugging in. X is 6, y is 3. Entonces, 6 times 3, cosine something. Cosine 6 minus 2 times 3. It's 18. Cosine, this is 6. 6 minus 6 is 0. Cosine 0 is 1. The answer is 18. Done. End the story. Any question? Super easy. So always you face one limit. You plug it in. See, the answer is the number 8 because the limit coincides with the function because it's continuous function. And you know que polynomial, trigonometric, exponential, rational inside the domain is continuous function. And the combination of the several continuous functions is multiplication, addition, subtraction, composition, division except denominator 0 is also continuous. The second question is a little bit more complicated. Is compute that limit. Okay. Entonces remember to face that problem. Well, you plug in. It's obvious that when you plug in is 0 over 0. 0 over 0 is indeterminate. Entonces indeterminate is synonymous to say no solution. I don't find the solution. The 0 over 0 is impossible. I need to do something in order to prove this. To say, remember, we can approach it in different directions. Approach it on the x-axis, linear first. So, for example, Go ahead.
Your audio is cutting out a lot.
Really? Let me see. Now it's increasing the volume. Now
yeah, I can hear you. Okay.
Thank you. And now, for example, I suppose so in order to convert my limit into variable, convert to the one variable to say you, for example, try to define one path. Okay, state relationship between x and y. For example, the most typical is y equal mx. This represents any line passing through the origin. Okay, the origin is the point 0, 0. So you replace, you convert this limit in another limit. Okay, include only one variable, like a calculus 1, que is x. And you replace y for mx. Entonces, 2mx times x squared. So replace y for y equal mx. This is x to the 4 power plus m squared x squared. Now in the top we have 2m x cubed. In the bottom we have well, x to the 4. You factor out y now x to the second, no? Because it's common factor. Because we have x squared plus m squared. And you cancel out, for example, here 2x and 1 here. Because the limit is so far is limited. and the x approaches to 0 of the 2mx divided by x squared plus m squared. And you evaluate, when you evaluate 0 here, and at the top you have 0, no? 2m, m is a number, it's a constant, times 0 is 0, divided by 0 plus something m squared. It's obvious it's 0, right? So in any direction, you prove somehow, in any direction, you approach it to 0, but the answer is 0. However, I suppose linear path. ¿Es enough? No. No. Entonces, okay, entonces recommendation is a typical example. Que you approach it, for example, for the parabola. Suppose you approach it to the parabola. Like that. Parabola like that. How do you know? Well, okay. When you are doing several examples, you see, for example, if you try to do something in order to put equal the degree of the polynomial in the bottom. So you have x to the 4th power and y to the 2nd power. So you define that y is equal to x squared, square double square become 4 power. So we have to the 4 power both in the bottom. Let's see. As you apply this, you have the limit when the x approaches to 0. So y disappear because you are doing that substitution, no? Entonces 2 y is x squared here, x squared, and x squared together is x to the 4th power over. In the bottom you have x to the 4th power plus x to the 4th power. Oh, this is the reason I'm using a square, because I need something in order to put equal the degree of the polynomial at the top and the polynomial at the bottom. Entonces es limited when the x approaches to 0 of 2x to the 4th power. Exactly, say 2x to the 4th power. And the limited one, que es obvio que es a constant, es 1. And 1 is totally different to 0. Okay, so what is the fantastic conclusion? This limit I prove que do not exist, because when you approach it to the parabola at the origin, we get completely different value when you approach a linear parabola. Any question? Any question? Do you follow me? Do you understand? Super clear. This is a moment. You in the lecture, maybe you understand a little bit, but it's a little bit confusing because it's new, and when you see again the situation, you understand much better. This is the idea for the review, and the test is similar. Well, not exactly the same, but it's similar, no? Similar to the review. Okay, number 3 question is about find domain of the function and express using set notation and do the graph in the xy plane. So we have one function. So number 3 is it's given one function. This function is actually, this is z. So f and the function notation f x comma y is z, but it's okay. It's a square root y plus square root x squared minus 1. And I need to find domain. And why not range also? Domain and range. Graphically, and what they want in set notation. Well, okay, or interval notation, either way. Let's do it in any way. So you see, well, this function is domain. The domain is a subset of R2, and the range is a subset of the R. Now the dimension for the domain is 2 dimension because it's xy, two independent variable, and the dimension for the range is only 1 variable because it's just c, no? Now, in order to find the domain, you suppose the supposition always is exactly the same called algebra. The supposition is the domain is totally R squared except the restriction, and we have restriction when the expression inside the square root is non-negative. Entonces es y greater than or equal to 0, because you know if the y, no, it's real. We are working with the real number. And x squared minus 1 greater than or equal to 0. Okay, it's x greater than or equal to 0. You manipulate a little bit this inequality. So x squared greater than or equal to 1. Apply square root both sides because my goal is solve for x. You can see, for example, this is, I don't know, actual value x greater than or equal to 1. Okay, this is synonym to say x greater than or equal to 1 and x less than or equal to negative 1. Okay, I suppose you remember very well how we solving the inequality. Involve actual value, no? Okay. This is the domain. Let me try to do the sketch of the domain. Well, I know that the domain is the region that satisfies this condition. And this condition is, well, first quadrant and second quadrant when the y is positive or 0, including the x-axis. And this is 1 here, greater than, and less than negative 1. This is our domain. Our domain is this region, and this region. This is domain. Okay, how we express this in interval notation? Well, interval notation, no, they want set builder notation. So it's easy. It's domain, D, capital D, is satisfy this condition, y greater than or equal to 0, and this condition, and this condition. Okay. Actually is or here. Entonces or. Let me erase this and. It's or. This and this together or. Another way to see more clear is, and the other notation domain is y. For example, y such that y is in between 0 and infinity, so like that, 0, infinity. And also x such that x vary from negative infinity, comma, negative 1, including negative 1, union, which union is or, equivalent to say or, 1, comma, infinity positive. Okay, this is another way using, interval notation, but they want in that way. Okay, it's much better in Calc 3. Graphic representation, this idea is this. Any point here belong to the domain. Any point here, no. Any point here, no. Okay, this is domain. And what about range? The question don't talk about range, but curiosity. Let's do in curiosity. Well, range is z value, and z value is the sum to a square root. Okay, I suppose I assume the component of the square root is the positive. So when you apply square root, you have to double sign plus or minus. But if you omit the sign, it's because I suppose que es positive, ¿no? Entonces C, o sea, the range es the C value que always is positive. Entonces es like Z greater than or equal to 0 maybe, depending on some value, suppose y0 and x equal 1, that corner. En that corner, que es 1,0, ¿no? O en that corner, que es negative 1,0. 0 en y, and 1 is 0, 0, 0 plus 0 is 0. So basically, it's this idea. Okay, in conclusion is the range is C value such that C vary from 0 to infinity. Any question, guys? Clear or confused? Super clear. Okay. Okay, no problem. Let's move on to the question 4. Question 4 is easy also. You see everything is easy now, huh? This is review, no? We go fast. And you see now easy everything. Number 4 is find the derivative. No implicit, no chain rule, no easy. Just derivative of the function that's given, okay, by the way, is fnx comma y is equal x squared plus exponential e to the x y. And then one, can you find, wow, the collection of the second derivative, so fxx, fyy, and xy, que by the way always is equal yx. Okay? Pero entonces we are doing step by step, no? You find the first derivative with respect to x. In this case, derivative this with respect to x is 2x plus something. And derivative the exponential with respect to x. Okay, you know that the derivative exponential is the same exponential. And derivative the argument, que es xy, with respect to x is just y. Entonces the answer is y e to the xy. This is the first derivative. The first derivative with respect to y, partial derivative with respect to y is, well, derivative of this guy is 0. And this is similar, but we have x e to the xy. Because derivative exponential is the same exponential, derivative argument with respect to y is just x. So you apply here the chain rule. But the basic chain rule, no complicated chain rule. Okay, now the second derivative, well, the second derivative, so you differentiate again with respect to x. Derivative this is 2 plus, and derivative this with respect to x is similar. In this case, y you consider a constant, no product rule, no, y is a constant because you differentiate now with respect to x. Entonces y, this y stay here, and derivative this is exactly the same. You are differentiation with respect to x. So now we have derivative with respect to the argument is y. So we have another y here to go outside. This is the first answer. Second derivative, xx. Second derivative, yy. Well, I focus in this expression. Okay, this is similar. This is similar because x stay here as a constant. This is e. And you differentiate with respect to y, this is x, is x squared. Nice. Now x, derivative xy, okay, by the way, is derivative yx. Let's do it in both ways. And verification, it's a good way to verification that everything we are doing is okay or no. So suppose that I differentiate first with respect to x, this. Now I differentiate with respect to y. Okay, entonces when you differentiate with respect to y, es obvio que that part is 0. And we focus in this. But in the product rule, you consider that this function is f, you consider that this function is g. Entonces, derivative f with respect to y is 1. Multiplication by e to the xy. This is the first part, plus. Okay, now the second part is y, stay the same, y. And derivative exponential, que is e to the xy and you differentiate with respect to y to say x, something like that. Okay. To verification, let's do it in this order. Y, x. So you differentiate these with respect to x. Again, we apply product rule. So it's e to the x y because derivative x with respect to x is 1 plus x times something derivative with respect to x is e to the x y, and derivative this with respect to y, the x, sorry, is y. And you can see that this and this expression is the same. Wow, fantastic. We are the best. Any question? Let's see. Okay, this is fine. Yeah. It's clear or no? Come on, guys. This is the moment. The review. Any detail that you don't understand, you ask me now. It's my pleasure to help you to understand everything, because on the test I cannot help. Okay. Go ahead. Go ahead. Way f of x is doing derivative f. Clarification. This notation is fxx. Okay, you differentiate first with respect to x, and you differentiate again with respect to x. See, it's this. You differentiate first with respect to x, and this. Or no fx. Fx is this is only first derivative of the function with respect to x, and this is second derivative. Second derivative with respect to x 2 times. Is it clear, mister, or no? Come on, activate the microphone and ask me any question that you want. Come on, guy. Clear or no? The notation is clear?
So wait, when you did f of x, y, or like x, y, you did it off of the fx?
So you differentiate with respect to x first and the y second. This guy. When in this case you differentiate with respect to y first and x second. I prove that always the ordering is not important. You get the same answer. Is your question, mister?
Yes, thank you.
Okay. So basically, in this problem, is one function is given, and you need to find the collection of the second derivative in different order. Differentiate x first. Again, take this expression as the first derivative. Differentiate again second derivative with respect to x. Likewise, y. So I differentiate 2 times second derivative with respect to the same variable. And now alternating. So I differentiate with respect to x and differentiate after with respect to y. Different order. So are you ready to face any problem similar to this? Sure. Good. Now, the number 5 question is about the chain rule. In the chain rule, we have function c. Okay, by the way, c, if you want, you replace by f of x comma y, or the letter you want to call the function, no? Okay, it's x cubic plus y cubic. And we have another relationship between another variable. X is equal u squared plus ub. And y is connected by u cubic time b. The situation that we have, I need to find what? Well, I need to find partial the c with respect to u, and partial the c with respect to b. So immediately I do the tree diagram to understand the chain rule. So the variable z depends on the two intermediate variables, x and y. and also x dependent of u and b, and y dependent of u and b. Okay, this is the tree diagram that expresses the connection in between the variable. Now, if you want to find the z du, the formula, the specific formula is this segment, this segment, this segment, and this segment. Okay, it's partial c with respect to x time partial x with respect to u. I did that part. Bam, bam. Plus partial z with respect to y time partial y with respect to u. Because we are working with the u, so you ending in u in this case. I know this is for this. Another no, depende B, entonces we are doing after. But okay, entonces we focus, we dedicate to compute separately this partial derivative. So this partial derivative is a partial derivative of this. Is differentiate this with respect to x. Es obvio que es 3x squared, correct? Es obvio que es 3x squared. And now differentiation x with respect to u, you take this expression. So when you differentiate with respect to u, we have 2u plus b, no? 2u plus b. A multiplication this and this. Plus differentiation c with respect to y is similar to this, pero 3y squared. Differentiation this with respect to the u is 3u squared b, no? 3u squared b. Okay, and this is the answer, no? Why no? Because I suppose okay, you need to express the final answer. So this is the z du using only the independent variable that we have in my problem. This is the independent variable. Entonces now, partial de z with respect to u is equal to 3 times x. But who is x squared? Is this expression. If you copy, u squared plus ub a squared, I did that part, multiplication by 2u plus b. Likewise, 3y squared, 3, this is monomial, and this is CC is u6b2. I take this expression, multiplication by 3u squared b. Guys, well, you can manipulate a little bit, but this is just stupid algebra, right? U multiplication this is 9, U 8, B3, and this is a little bit more complicated. You expand this, and you FOIL with this. Oh, I don't care. This part is not important for me. Okay, I know that you know that part. Any question on this manipulation? This is the okay. This is the okay, or another possibility. Say my paper. Look at my paper. I leave it like that. 3u squared plus ub squared multiplication 2u plus b. I don't do that part because I consider it boring. Plus 9 u8 b3. Something like that. Okay. The other branch is similar. In order to find the CDB in the tree diagram, you moving to this trajectory. Look, this and this and this. Therefore, dz dv is equal dz dx time dx dv. So I go to this trajectory plus dz dy, I'm moving for this, time this y dv. Okay, entonces this, wow, I did before, is this. This, no, because you differentiate with respect to u, but now you differentiate with respect to b, and when you differentiate with respect to b, this is a constant, and this is just u. And this, well, I did before, 3y squared, and this is the derivative y with respect to b, que es just u3. Okay, so what is the final answer? The final answer is, well, this CDB is equal to 3 times, and x I know is u squared plus ub raised to the second power, multiplication by u. In this case, easy manipulate algebraically, plus, this is 3, but 3 u, what the hell is u? U is this. This is the square, is u6 b2 times u3. Okay, this is relatively more easy. This CDB is equal to 3u u squared plus ub squared plus 3 times u9 b2, something like that. Any question? Any question? What part confusing? Come on, guys. Don't be shy. Chain rule. One problem of this in the test. You can see. Chain rule. Super clear? Follow. Clear. Good. Okay. Now let's move. Let's practice a little bit about implicit differentiation. Implicit differentiation. So we have this expression. Okay, this is number 6. Okay, it's 2x squared plus 3y squared and plus 4c squared is equal 5 xyz. And they want you find partial c with respect to x, and partial c with respect to y. They want. Entonces es obvio que we need to apply the implicit differentiation formula, because it's a little bit crazy isolate c in this equation, no? Entonces no, you trick like implicit. So you copy something like that. 2x squared plus 3y squared plus 4c squared minus 5xyz, and you consider que this is the capital F function que depende x, y, z. And this is always equal to 0 because the implicit is defined under the supposition that the equation look like that. Entonces, in order to find the partial c with respect to x, well, the formula is minus capital partial the implicit with respect to x divided by partial with respect to z. This is the formula. Likewise, partial to z with respect to y is similar minus capital F differentiate with respect to y divided by differentiate the same function with respect to z. Let's do it quickly because it's too easy. You put the minus here in the front. If you want to manipulate in order to eliminate this minus, and you differentiate this expression with respect to x. Entonces I can see derivative of part is 4x. Derivative of part is 0, derivative of part is 0 because you are doing differentiation with respect to x, no? And derivative of part with respect to x is 5yz. And derivative of x with respect to x is 1. Entonces es minus, ¿no? Es minus 5yz. Good. Now differentiate with respect to z. This is 0, this is 0, this is 8. AC minus derivative, this is only 5xy. And this is the answer, right? Oh. So you don't like this negative, okay, you change. You suppose que 5yz minus 4x divided by az minus 5xy. So the thing I did was multiplication by -1, the top part, or the bottom part, it doesn't matter. I select the top part. See, you select the bottom part, you get the equivalent answer. Okay, let's do it in the second. The second is minus. And you differentiate partial derivative with respect to y. This is 0, this is 6y. Minus 5 xz, because in this case you consider a constant xz and the y is the only variable, and derivative y with respect to y is 1, okay. And this is exactly the same. This just copy and paste here. If you want to eliminate this negative, well, okay, let's do it. 5xz minus 6y az minus 5xy. Done. End the story. Super easy. No big deal. No big deal. Super straightforward. Guys, you know my way. In the test, I put easy example. No sophisticated. Okay, you are undergraduate students. Now, in the online, yes, a little bit more complicated. Not complicated, but a little bit different. Using your imagination, try to go to the help for the my lab, and you ask me in the homework. If you have any question, directly with me in the tutoring, or you email me the screenshot, no, with the specific question I want to help you. And the test, no, I cannot help. Any question? Number 6. But see, it's clear or confusing? Very confusing. Very clear. Totally confusing. No. Very clear. Okay. Let's move into 7. Well, in 7, we apply our knowledge about the maximum minimum. And this 7 is about local. Local, remember, is without restrictions. We have no restrictions. So the domain for our problem is all real number. All real number, no. In 2 dimensions is R2. Therefore, no limitation, no restriction. Entonces we have function. And the function is x cubed y plus 12 x squared minus 8y. I need to find the potential, I don't know, local mean, local max, or saddle point. You know what is the idea for the saddle point. So remember, the step number one is find the first derivative with respect to x and with respect to y. You enforce it to be 0, and this allows us to find the critical value. Okay, so this is differentiate this with respect to x is 3x squared y plus differentiate this with respect to x is 24x, and differentiate this with respect to x is 0. Okay, and you put it equal to 0. The second derivative, the next derivative, is the first derivative with respect to y, is x cubed. Derivative this with respect to y is 0, and derivative this with respect to y is 8. Okay, easy. I like that because this is one equation que contains only one variable, no system. Entonces es obvio que the solution for this is x equal to, no? Easy. No complicated. Now plugging into here in the second equation. Entonces is 3 times 2 squared y plus in this case is 24 times 2 should be 0. This is 12. 2 squared of 4 times 3 is 12y plus 48 equals 0. Es obvio que y es negative 4. Okay, entonces I discover que our famous critical point is the point 2, negative 4. It's critical value, critical point, the way you want to call it. Okay, remember the definition is when both derivatives are 0, in this case, or do not exist. So I need to find the nature because I'm using the second derivative test. It looks like that. It's a mean. So it looks like that. So the two curves I try in one dimension hard is the first derivative with respect to x in x direction and y direction. Or another possibility, when you're increasing the dimension of the problem, increasing the complication, so you suppose you have this situation and this situation. One is positive, one is negative, so it's other point. To verification this, we apply the second derivative test, because the second derivative test is a little bit complicated. No complicated, but it's different. It's not obviously like Cal 1. You compute the collection for the 3 second derivatives, fxx, x, y, and fxy. Okay, by the way, it's equal fyx. So you need to compute it only in one way, not necessarily in both ways. Okay, so the differentiation this with respect to x is 6 xy plus 24. And the second derivative with respect to y is this with respect to y. We have no y here, entonces 0. Entonces now the crossed derivative, derivative with respect to x first, I did that. Now with respect to y is just 3x squared, something like that. Because when you differentiate with respect to y here, derivative y is 1, stay 3x squared, you consider constant, and we have no y here, it's 0. Okay, entonces you evaluate, okay, let's do it one by one. You evaluate xx at our specific point, que es 2, negative 4, no? Entonces is 6 times 2 times negative 4, que es y, plus 24. Entonces this is, let me see, this is 48, no? 48, negative 48. Negative 48 plus 24 is negative 24. And y is 0, independent of the point. is 0. And this is xy, yx, and the point 2, negative 4 is 3 times 2 square, que es 12, ¿no? Es 12. Entonces, the discriminant, que es capital D, the formula is fxx times fyy minus fxy squared. This is minus 24. We compute numerically. This is both 0. Multiplication by 0 is 0. Minus, and this is 12. This is 12 squared. It's 144. That says minus 144. And you know, when the discriminant is negative, it's automatically solved. So the only critical value que we discover, que es 2, negative 4, actually is no min, no max, es saddle point. End of story. Any question? What part confusing? Guys, the organization is clear. You face the problem of the minimum maximum in multi-dimension. You find the first derivative with respect to x. You find the first derivative with respect to y. You focus it. D is positive or negative. What happened? Okay. Let me recall. The second derivative test in multivariable is CD is positive and fxx is also positive. We are talking about evaluate at the critical value, not in all real number. Entonces, this is mean point, minimum, local minimum. CD is positive and fyy is negative. Entonces, this is max. CD is negative. I don't care the rest. Automatically, the saddle point. And CD is 0. No conclusion. Okay, I explained super clear in the video I posted for the June 7. Entonces, hello, you don't watch the video or you don't be present here in the lecture. No. This is the moment to reinforce any situation. No, anything you can ask me, don't hesitate. Okay, go. Okay, entonces, summarize quickly. You take the function. You compute the partial derivative with respect to x and with respect to y, and you enforce it to be 0. In this moment, you have a system of equations. And this example was easy because one equation contains only one variable. Nice. I am looking. Entonces, you find the critical value. Entonces, you need to determine the nature of this critical value. Si es maximum, minimum, or saddle point, or no conclusion. And to do that, you compute the collection of the second derivative, evaluate specifically in that point, boom, and you computed the formula, that formula. See, that formula give me positive. Well, I need to verification. Wait, I'm making a mistake here. This is XX always. Sorry, no YY, never. Okay, to say you compute the second derivative with respect to x 2 times, only that. And this give me the information si es minimum or es maximum, si es positive. Si D es positive, the confirmation que es minimum is because the second derivative with respect to x 2 times is positive. Si es the second derivative with respect to x 2 times es negative, es max. Si discrimina, que es D, es negative, no, definitely I don't need to see anymore, es saddle point. Okay? It's super easy. Super easy. Any question, guys? No? Good. Everyone follow me? Okay, I need to see your face. Wow. This is important day because it's a review. I don't know if we finish or not today. If we don't finish, no problem. We continue Friday, no? The review. This is important. Okay, everyone pay attention. Everyone ask me any question. Okay. I follow you in the my lab. Some students are doing good job. Another student, I don't know what happened. I need to know. After the second test, I need to make a decision. Si you stay here or I drop you. Well, I propose you. Si you continue, okay. Si you see that your performance is too low, you want to continue, you know what's your grade. See you make a decision to drop the class, okay, without penalty, I don't know. This is detail I don't know exactly. Okay, so this is important moment. Second test is super important moment to definition of your behavior in this class. Okay, let's move on to the question 8. Question 8 is about, in this case, different. It's minimum, maximum, pero es global, or absolute minimum, absolute maximum. Okay, what is the idea? Absolute maximum, absolute minimum. Well, the idea is you find also the critical value, pero you don't using the second derivative test. No, because our domain is limited by the one specific region. Then you find the critical value. See, the critical value lie inside the region is perfect. See, the critical value lie out, no, I don't care. Entonces, the critical value que lie inside, I don't apply the second derivative. No. Why no, professor? Because my goal is find the global maximum and global minimum. So you evaluate in the original function this critical value plus the boundary. So any point in the boundary. So I want to explain how. Basically, it's important in the different boundary. You try to find, so you reduce the dimension for the problem in 2 dimension and 1 dimension, like a calculus 1, and you determine the potential maximum or minimum. It lie on the boundary, and also don't forget the corner of the boundary, and you evaluate everything, and you create a big list. And when you create the big list, you take the large value as the global maximum, and the smallest is the global minimum. And the story is super easy. So in the question 8, the function is 1 plus 4x minus 5y. Entonces I want to investigate the behavior of this function in the region whose vertex is 0,0, 2,0, and 0,3. Wow. By the way, guys, what surface it is? What surface it is? I need to know the name. What surface it is? To see much better, you assume that f of x, y is z. So see, you put in another problem without maximum, minimum. This equation, c is equal 1 plus 4x minus 5y. I ask you what surface it is. Come on. Es ellipsoide, es paraboloide, is cylinder. What kind of cylinder? Cone. Nobody know that? I don't know. You don't know that. Okay, because it's super easy identification. It's only, memorize elementary piece of information to identification. Paraboloid. Okay, Javier say paraboloid. Another opinion. Come on, Danny, Giraldo. You always get the answer for the surface. It's a Blake. Ese plane, how do you know que ese plane? How do you know? How do you know que ese plane? How do you know que ese plane? Gerardo say que ese plane. It's no C there. Yeah, in the plane here we have C. So what is the general equation for the plane is AX plus BY plus ZZ equal D, no? This is the general equation for any plane. But the most important thing is that the exponent of the variable is 1, is linear, is flat. That is the reason that this surface is flat. And so you see a square, something. Well, so you square something. Entonces now it's a curve. No curve, surface, pero curvy surface. Okay, and entonces we study, see everything is a square and everything is positive. This is called ellipsoid. I look like the football ball. Si one is negative, entonces hyperboloid 1 chi, 2 chi, blah, 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 blah. Si the right hand side is 0, is a cone. This is the way, guys, to identification this. Okay? And this is important, extremely important. So you don't know that, you are in big trouble in the next chapter, because the next chapter is integration, and the integration we need to determine the region in 3D in which you can set up the integral. Okay, therefore it's important that you are familiar. Not all surface, no, it's crazy. Okay, so all surface we have GeoGebra, and GeoGebra you put the surface and you see approximately what the idea. Pero intuitiva idea, si es a plane o es a surface o es the cylinder o es something, no? Is clear or confusing? Do you understand or no? You are totally lost with the surface. I don't know. Always happen when I teach in that class. The student is very reluctant. Okay, I understood. Okay, Javier. The problem, Javier, is that you don't forget. Okay, you understand what I explain now, no? But you forgot. Bah, or you don't know. I suppose that you don't. Another student, not forgot. Okay. So now let me do the sketch of the our region. Okay, I want to investigate my behavior of this plane. This sake is the corner 0,0. 2,0 here. And 0,3. 1, 2, 3. When we connecting this corner, I suppose we have the triangle like that. Our region is something like that. So inside the region, not outside. So I don't care at one point outside. No, inside the region, I need to investigate what is the global max mean. Okay, entonces I start always try to find the local, because suppose, I don't know, in other problems you see before in the lecture, I encourage you, like you see the video I posted in the lecture of the June 7. So maybe we have here 1 point is maximum inside. But how do you know that? Well, you find the first derivative with respect to x. You find the first derivative with respect to y, and you enforce it to be 0. The first derivative with respect to x is 4. Yes or no? Derivative 1 is 0, derivative for x with respect to x is 4, and derivative negative 5y is 4. And 4 never is 0. Likewise, when you differentiate with respect to y is -5. That means that we have no critical value in this problem. So not always we have. No critical problem. I'm making sense. Because my function is a plane. My function is a plane. Yeah, I know that the plane is flat. Si the plane is flat, we have no maximum minimum. Because the plane is flat. So we have no that mountain and its valley. Makes sense, right? I don't care for the point inside, because inside we have nothing. Because I care in the boundary. Let's see what happens in the boundary. You take any trajectory. Suppose this, I travel in this trajectory. And this trajectory is x equals 0. You travel on the y-axis, x equals 0. Entonces, x equals 0, and my function is f0, y. So use substitution, x equals 0. Entonces, my function is y minus 5y. I call this function like a f1, okay, depending only the y, no? So I eliminate, so I make the reduction of the dimension for the problem when you declare que one variable is 0. Bueno, in this case 0 because in our problem is this, pero x equal a constant, not necessarily 0. X equal, suppose que another problem is x equal 1. Entonces, pero you plug in 1 here, entonces now we have only one variable. Suppose I want to investigate here, see we have or no in middle of the process one critical value, no? Entonces, this is calculus 1. You differentiate 1, the function 1, with respect to y, okay, by the way, again, it's minus 5, and never is 0. Wow, entonces, what the hell is that? I don't understand, professor. Bueno, okay. Entonces, in the list, in the famous list, that we finish any problem of the global maximum, global minimum, you listing the endpoint. So the corner, this corner, and this corner. Because I discovered in the middle, we have no maximum minimum. So, see, I see this in 3 dimensions. Remember, one more time, the function is flat. When you evaluate, for example, the function in 0, 0, in this corner is 1. Look, is 1 because 0 and 0 is 1. So I want to declare, for example, here the value for the function and the c. Que c you don't see now because c is the axis que es perpendicular to the whiteboard, no? So I declare que c is equal to 1 in this corner for the function. Entonces the point is 0,3 is 1, 0, and negative 5 times 3 is negative 15. Entonces negative 14, no? So this C value is negative 14. I suppose que ese plane, no? Ese plane, pero this plane have inclination. Entonces when you go in this direction, for example, it's ascending because go from negative 14 to positive 1 in the Z-axis. Okay. Let me continue on this. For example, let me change the color. No. Let me change blue color. I try to do easy. I know that I need to travel also for the hypotenuse of this triangle. No? Okay. This is y0. So the function is, so I assume that y0, the function is 1 plus 4x. I call the function 2, que depending only of the x. When you differentiate this, because I want to investigate, see, in the middle of this blue path, we have maximum or minimum local, the derivative 4, and 4 never is 0. Again, the false of this, so what is the responsibility of this? Because it's a plane. The function is a plane. See, the function is a plane, everything is easy. And you evaluate in our list. Okay, I forgot here, I forgot here, but I don't put in the list, it's the most important part. You evaluate F, evaluate in, well, no, I don't need to evaluate 0, 0 again, no? It's in 2,0. 2,0, 2,0 is, look, is 4 times 2 is 8, y is 0 is, entonces es 9, no? Es 9. So the value for the function C in this corner is 9. Well, entonces I do walking finally for that direction. Well, I investigate that the equation for this line is y equal minus 3 over 2 x plus 3. This is easy, no? For us. You have 2 points, you compute the slope. Okay, so because the slope is negative, because it's going down from and the y-intercept is, this is the equation for this. So now, the only thing I need to do is replace y, this y, here, in the function. So suppose now that you navigate for the line y equal minus 3 over 2x plus 3. So we have a function, okay, called f3, okay, depending only of the x, no? Because you replace y. Okay, you for example, okay, let me try. The function, the original function, you replace x stays the same, but y no. Y now is minus 3 half x plus 3, and we get the new function, okay, called f3, okay, depending only of x. Okay, I did that algebraically. Fn3x is equal, when you plug it in and manipulate algebra, is 23 over 2x minus 14. I suppose, and this matching perfectly with the corner. Oh, well, no, okay. You find derivative, because again, I want to investigate. Derivative 23 over 2, okay, no 0. That means in this trajectory, we have no local maximum, local min. It's impossible. It's a contradiction. However, in the corner, you can evaluate, but I did that. Because I did the red part, I did the blue part. So it's repetition again, but just in case to verification, let me see at x equals 0 is negative 14. Look at that. And x equal 2, well, 2 plugging into here, 2 cancel out. It's 23 minus 14 is 9. Perfect. Okay. Entonces I don't need to do any more. Just what is the global? What is the global mean and what is the global max? It's obvious that this is the global mean, negative 14, and this is the global max. End the story. I finish. Super easy. Well. See, the function is no plane. It's a curve. Entonces more complicated because when you travel for the boundary, maybe you have, maybe you have a local max, local min. Maybe. Okay, super. Any question? Do you understand this or no? Confusing? Okay, in the test, I don't put one similar, no complicated. Because this is, I complicate it too long, problem, no? It's not too long, it's easy. Okay, so let's move on to some example of the Lagrange multiplier. Lagrange multiplier, remember, is another way to analyze max minimum when you have constraints. So in this problem, in number 9, say, find the point of the curve, number 9. Find the point of the curve xy equal 1 that is closest to the origin. Using Lagrange multiplier. Wow. Okay, what is the idea? It's xy. The function x times y equal 1 is synonymous, is equivalent to say y equal reciprocal function. A reciprocal function, you know, can look like that. It's a hyperbola. Hyperbola. And this is the origin, 0, 0. 0, 0. And I need to find the closest close point. We can use intuition. It's supposed to close point look like that. This is x, y. Another point here is not close. The distance is bigger, right? Actually, the thing we are doing is, remember, to apply Lagrange multiply method, we need two equations. We need the objective function, Okay, the objective function is the function that you want to optimize, minimize or maximize. In this case, minimize because it's closest. Entonces, the objective function is normally expressed like f of x, y, no? Is the distance from any point on the curve is this, and the origin. This is super easy. Distance formula is equal to square root x squared plus y squared. This is the objective function. I want to simplification a little bit because you consider the square root. The differentiation is a little bit more complicated. However, it's synonymous if you consider the distance or the distance square. So it's easier manipulate algebraically. So when you minimize this function que es the distance square, you minimize the distance. It's the same. Entonces, the constraints is the condition, okay, in this case, the function que es x times y equal. Entonces, you express it in Lagrange multiply language. You express it like a gx, y, but you express it like a implicit form. Entonces, x, y minus 1 equals 0. Wow. Objective function, constraint, expressed in the language of the Lagrange multiplier. Super. No, entonces Lagrange multiply say, well, okay. If you want to determine the, wait, what happened with the square root? Okay, the problem talking about closest point, and closest point is the distance, and the distance of course contains square root. However, I am smart. Yeah, I know que si I introduce in the objective function the square root, it's more complicated. Compute the gradient. It's the partial derivative with respect to x, partial derivative with respect to y. But I know que si the distance contains the square root, the distance square do not contain the square root. And this function is easier to differentiation than this. And they are not proportional, but they are the same equivalent meaning, right? So you minimize you want to minimize distance, but you minimize the distance square. It's the same. It's the same objective. We go to the same objective. It's clear or not? So I'm smart. Yeah, I try to avoid the square root. This is clear or confusing? Okay, this is the engineer intuition guy. So you don't need to complicate your life with a stupid square root. See, I want to close. Suppose que the minimum distance is f5. df5. So the n will take square. No. Well, no. Okay, yes. You want to find the minimum distance? Yeah. Actually, yeah. It's because the relationship between my new objective function and the distance is a square root. You find suppose you need to find the minimum distance, no? And the distance can you find after the minimization or minimization, f5 or f25. Entonces actually the distance f5, no, square root 25. Yeah. This is the idea. So I eliminate the square root because I want to make easy the objective function. And this is the same behavior. Okay, let's focus in the Lagrange. Lagrange say, wow, Lagrange formula, say. The minimum and maximum of the function subject to some constraint is equal the gradient of the function is parallel to the gradient of the constraint. To be parallel means que you multiply this by the number que Lagrange called lambda. Entonces, multiply is a number. I proved in the other class que en the minimum and maximum, the gradient, que es el vector of the function, and the gradient, que es another vector of the constraint, are parallel. The problem is that you introduce, unfortunately, a new variable in our problem. So I need to find x and y. This is my final answer. But you introduce a lambda, and lambda is not important. I don't care who is lambda, because it's a multiplier, a number. Maybe it's 2, maybe it's 20, maybe it's radical 5. But okay, fortunately, we have this. Okay, but entonces you separate the components. So our problem is 2 dimension. This is component x, component y. You know what is the definition of the gradient. And this is the component x, component y. Translate in one common easy language. F of x is equal lambda g of x. That's my first equation. My second equation is f of y is equal lambda g of y. But you have 3 unknown, x, y, and lambda. So we're using the constraint. The constraint is x, y minus 1 equal to 0. In this case, we have a system of equations that contain 3 variables. It's non-linear, so always. Entonces, I explained in the last class how you solve it using Wolfram and alpha. Let me try to do without, well, let's do it in both ways. Because today a review, I need to practice. No? Okay, let's focus in the gradient component of the f. Bueno, you know que partial derivative with respect to x is 2x. And partial derivative with respect to y is 2y. That's it. This is the gradient. Gradient of the g. Well, a partial derivative with respect to x, que es y, because with respect to x with the derivative with respect to x is 1, y you consider constant, pero constant like a multiplier, no? And this constant, que es negative 1, is addition or subtraction, entonces 0 desde este. Coma, and now derivative with respect to y, que es x. Done. This is the gradient. Okay, you put each other together. So my system of equation is 2x is equal lambda y, this component equal this component, equation number 1, similar to this. 2y equal lambda x. It's a lambda, sorry. Lambda x, equation 2. And the second equation is, well, xy equal 1. I put it equal to 0 or no, whatever. Yeah, this is equivalent. This is my 3 equation. This is my 3 equation. This is my 3 equation. I need to solve it. I want to solve it algebraically by hand. Pero no. In the test, no. In the test, you are doing by Wolfram alpha. But let's do it by hand because in this case, it's easy. In other, no. But in this is easy. Okay, remember, lambda is not important. Parameter. I don't care. If you divide equation 1 divided by equation 2. So normally, this situation is regular happen. You have 2x, divided by 2y is equal lambda y divided by lambda x. 2 cancel, lambda cancel. And stay alive, x over y equal y over x. You apply cross multiplication, and you have y squared equal x squared. Therefore, x equal y and y equal x. Well, actually, is when you apply square root both sides, it's absolute value y is equal absolute value x. Okay, this is or plus or minus, but in this case, plus. Okay, now I come back to the equation 3, okay, I never use it. So x and y is the same, so x squared equal 1. Apply square root both sides. Entonces x is equal plus or minus 1. And y is also plus or minus 1 because it's the same, no? The absolute value. This is the same idea when they complete the signs. But we have 4. 4 points, no? We have 4 points. And some point is impossible. Suppose the point 1, 1, and the point negative 1, negative 1. Because look. Suppose the alternating sign 1, negative 1 and negative 1, 1 do not satisfy the third equation because this is positive 1. So when you multiply positive is positive, or negative is positive, but negative and positive is not positive. Like this point you discard, no good. And you focus in this. Focus in this. Okay, so the point is 1, 1. But I determine who is the maximum and who is the minimum. Okay, and remember we need the minimum, no? We need the minimum. In this case, what function? The objective function. I go to the objective function. I go to the objective function. The original is distance. Distance is square root x squared plus y squared. In our specific problem is 1, 1 and negative 1, negative 1. Substitution here is square root, and this is plus and minus 1 square plus and minus 1 square. Wow, it's radical 2, no? It's radical 2. So the minimum distance is radical 2. And make it sense according to this sketch. Look at that. This is not necessary to do a lot of complicated problems using the common sense. That guy, when you become engineer, always we using common sense. And the mathematics guys support can help me to understand exactly what's the problem. But suppose that this point is 1, 1. And this point is a point negative 1, negative 1. We have no parabola here in the second quadrant and the fourth quadrant. No. And the distance we are talking about is this distance. Okay, is 1 here, and this is radical 2 in both directions. This distance is radical 2, and this distance is radical 2. Any story? Any question? Okay, entonces I spend the rest of the time try to do the system using Wolfram alpha. And we continue on Friday working in the Lagrange, because Lagrange is important, in my opinion, no? It's important. So the rest of the problem, we are doing Lagrange, more complicated problem. To say always we are solving the system. In this case was easy, but in this case no, using Wolfram alpha. Let me try using Wolfram alpha. Okay, I want to find my Google Chrome. Wolfram alpha. Wolfram alpha. There you go. I found. I explained the last class, guy. Let me share the screen. Screen. Share. Wolfram alpha. There you go. Bam. 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 Do you see Wolfram alpha? Good. Now, okay, I open algebra. I open this. We have different here. The system separated by comma. Either way, I explained the last class using this. This is fantastic. Everything working perfectly in Wolfram alpha. I encourage you to try to discover. You put a solve, and you listing equation by equation. My first equation is 2x equal lambda y. But we have no lambda here. We have L, capital L. I recommend capital L, like a lambda. So in Wolfram alpha, no lambda, capital L. Time, there's a border on this time because you omit this time. Wolfram alpha understands that the combination L and Y together without multiplication sign in between is considered like one new variable, que es Ly. No, this is wrong. Entonces you separate by and the different equation. The second equation is 2y. In this case, when there's number and variable, not separated by time. Or not necessary. When it's equal lambda is L I x. This is my second equation. And my last equation, okay, the constraint is either way you put x times y minus 1 equals 0 or equal 1, doesn't matter. Boom. We have a collection of my equation. I press this button, compute the input. Wait some second. Sometimes give me imaginary solution, but I don't care imaginary solution. Okay, entonces I care in the two last part. Que in this case lambda is 2. And the x is -1, -1. And L is 2 again, and +1, +1. Entonces, in order to find si es mínimo or maximum, you plug it in into the region. In this case, it's a minimum because both is the same. It's a square root 2. And using the common sense and the imagination and the graph, you see that this distance is minimum. Super clear? Super clear? Come on, answer me. Answer me. Super clear. The rest is okay? Wait a second. Let me see. Stop sharing. Clear low. Carlos, okay. I want to hear opinion. How do you feel? How do you feel in this test? How do you feel? Okay, I send the test. You start working if you want. It's super easy. All good, professor. Okay, good. This is what is that? Anne Cruz. I'm in the last class. I don't see your face. Anne Cruz. Okay. Charin, Marco, Hadi, Brandon, Leonardo, Omar, Alejandro, okay, Daniela. Entonces, right now, when I create the video, I will post it in YouTube, and you watch it again if you want. Okay? Okay, guys, I stop recording.